Good evening. So hi everyone, and welcome to the Winter 2024 George and Maureen Ewan Lecture. I'm Mark Richardson, the Manager for Education and Public Outreach from the Arthur B. McDonald Canadian Astroparticle Physics Research Institute, a community of scientists, universities, and research labs across Canada, uncovering some of the biggest mysteries of the universe by looking at some of its smallest things, and sometimes we have to go underground to look at those things, as we'll hear about tonight. So thank you all for coming. I want to recognize that we are here on the lands of the Cataraqui, now Kingston, the traditional lands of the Anishinaabe and the Haudenosaunee peoples, and many Indigenous peoples before them. I'm truly appreciative that we are all able to learn tonight from this beautiful location on Lake Ontario, even with the blustering cold out there. I'm glad you were all able to get in and get some warmth. So I'm from Halifax, and after some research, I found out that is the traditional land of the Eskikawak, traditional land of the Mi'kmaq. And I reflect on that because Kingston, much like Halifax, it's a land on the water. It has some nice and fairly dark skies above. And I'm personally an astronomer and someone who revels in the wonders of the land around us, the planet Earth itself, the skies, and the universe above. And so I'm really looking forward to the talk to hear about that universe. And I recognize that this science relies on facilities and that use traditional and sacred lands of various Indigenous peoples who have a voice to add to this science and who should be gatekeepers to these spaces. So to all of you, I urge you to think of the connection you have with the land around you and the gift we have to learn wherever we are, including from the dark wintry skies above. And even though it's winter, I do encourage you to find time to enjoy these skies, maybe on slightly warmer nights, as the nights are, maybe thankfully, becoming a little bit shorter as we move towards spring. And so I hope even through the snow, you do find the opportunity to also learn from the land around you and to connect with these beautiful lands. And I encourage you after tonight to maybe explore websites like whos.land and learn about the past people who have lived where you lived. And so moving forward, let's reflect and work towards the decolonization of these spaces to make them ones of friendship and access for all those in our community. Now, as I said, this is the Ewan Lecture, where we will hear from Dr. Art McDonald, but I would first like to welcome up to the front Dr. Tony Noble. He's a professor from the Queen's Physics, Engineering Physics, and Astronomy Department, and he is the scientific director for the McDonald Institute. And so he's going to say a few words about the Ewan Lecture, George and Maureen Ewan, and the lecture that bears their name. So thank you, Tony.
Thank you, Mark. Well, it's my great pleasure, actually, to also welcome you here. And it's interesting that in contrast to Mark's words, what I wrote down was such a beautiful day, sunshine at last. Anyway, I wanted to say a few words about the George and Maureen Ewan Lecture series. So if you go back to the 1980s, when hair was a thing, there was a great problem in science, and that's what Art is going to talk to you about tonight. But George and a few other visionaries had a wild idea on how to address that problem. And that was really the birth of astroparticle physics in Canada. Right now, there are hundreds, literally, of scientists across Canada occupied with this research. Many of them are funded through the McDonald Institute, which is hosted here at Queen's, but is distributing resources all across Canada. And that work is work that is globally recognized as being the highest priority work in science today. So George was a founding member of the SNO experiment and a wonderful human being, and I think Art will say a bit more, but as a mentor and as a colleague in the department, he was just such a warm and enthusiastic and intelligent person to have in our community. And he was a pioneer in both nuclear physics and the astroparticle physics in Canada. Maureen was also very active at Queen's. She was an advocate for the well-being of others and a fervent supporter of the Bader Centre, which many of you will know, and she enriched the lives of countless women that she interacted with there. So they wanted to create this lectureship. It was made possible by a generous donation from George and Maureen, and their vision really was an opportunity to bring the public in to meet distinguished scientists from all around the world, and at the same time have an opportunity to have a really good engagement with all the students and faculty and postdocs at the university to interact with that person over several days. So that's what we're trying to accomplish with this, and this is the public lecture part of that. And now it's my great pleasure to introduce Professor Art McDonald, who is the George and Maureen Ewan Distinguished Lecturer for tonight. So Professor McDonald was born in Cape Breton, Nova Scotia, and I have to say has never forgotten his maritime roots. And those roots, along with his wife Janet, who I think is over there, have kept him firmly grounded. In fact, I have heard Janet say on more than one occasion, "You're not a real doctor, you know." So Art did his undergraduate work at Dalhousie University in Halifax, and he was inspired by the physics professors that he had in first year to pursue physics. So I know a lot of my students from first year are here, so pay attention. He then obtained his PhD in physics in 1969 from California Institute of Technology, Caltech, working with William Fowler, who went on to get a Nobel Prize of his own in 1983. Art then moved on to become a research scientist at Chalk River, not far, well, an hour or so out of, near Deep River, not far from Ottawa, and then took a professorship at Princeton before he was recruited back to Queen's. And he was recruited back to Queen's in 1989, where he has stayed ever since and where he is still incredibly active. So Art has far too many awards to list. He's a member of every society and every distinguished position you can think of. I was going to try and challenge myself to memorize them all, but I gave up. But really, the work that he led on the snow experiment led to the Nobel Prize in 2015 for the recognition that neutrinos have mass and that they oscillate. And that was followed immediately afterwards with the 2016 Breakthrough Prize. And so you didn't come here to listen to me, so it's my great pleasure to invite my friend and colleague, Art McDonald, to present his lecture on knowing the universe from a hole in the ground. So please, Art.
So this is a great honor for me. George and Maureen were great friends, and George was a tremendous mentor for me. When he left Chalk River to come to Queen's and shortly thereafter be the chairman of the department here, he opened up a position at Chalk River, which I ended up occupying. And we worked together for many years between then and 1989 when at that point, he was about to retire here at Queen's, and so they were looking for someone to replace him. And again, I ended up getting that position. And so I've often said, if you want to have a good career in physics, follow George Ewan around. But he's everything that Tony said, a wonderful person, a great scientist. He's actually the first person to use a germanium detector, which these days is a fantastic tool in medicine and many other ways in science, and has an award for that, as well as his many contributions to the SNOW project. So what we're going to talk about today, in addition to the sort of things that George provided, is the other things that we can learn from what George started, which was going underground to get the lowest radioactivity location you can get. Maureen is also a good friend, and her work at the Ben-Rie Center is still remembered and noted. She was just a very warm individual and helping the female component of the Queen's faculty and mostly undergraduates and graduate students was what she was extremely good at, and she's fondly remembered for that as well. Back in 1984, there were 16 of us that came together to start this project, plus a number of others who joined shortly thereafter. You can see some names here. I was looking around before we started this evening. Ewan Lecture is here. He's in the picture in the front row, third from the left. I have no idea if Peter Gensved's here. He might be. Barry Robertson is another one. Hamish Leslie, I know, is here. He joined a little bit later, but is a stalwart in terms of the development of the project. Bill McClatchy is here. I was just speaking with him before the project. For the lecture, we were talking about the contributions. And really, this has been a team effort from day one. And George was a great team leader and started it all off. And I have a Nobel Prize for this, but I'm very conscious of the fact that they've given this to the team leader, but really it's the people who developed the project who did all the work. And there's a significant component of that from Queen's faculty, students, postdocs. We have a total, over the course of the SNO project, which took many years, a total of 200 graduate degrees and postdoc experiences, of which we're very proud. And we have, I think, 35 faculty positions around the world from people who worked on this project. And I'm very pleased to say 35% of those are for women, which in physics is a very good record. So this is an educational experience as well as a research experience. But it's really a fun opportunity. It's the sort of thing where you can learn a lot about your world. And very often in science, if you're trying to do something new, what you need is to have something that's quite unique. And in Canada, we have something that is quite unique, and that is the underground laboratory that we have in, might be better if I turn this on, there. The underground laboratory that we have in Sudbury is referred to as SNOLAB. Sudbury Neutrino Observatory has often been called the SNO project. And it's an extension of what we did during the creation of the SNO project. And that is, it's not only deep underground to avoid cosmic rays, but it's also ultra clean. And so in that circumstance, we're able to do some rather unique things. We use particles such as neutrinos, that we'll discuss in a bit, to probe, for example, as in the SNO project, the core of the sun. And that can tell us about the sun, it can tell us about neutrinos, it can even help us with other things here on Earth. We're now, there's an operation of an experiment called SNO Plus that now has the capability of studying neutrinos from the Earth. And it turns out that 40% of the heat flow out of the Earth comes from uranium and thorium decay. And that produces neutrinos that we can measure. We're also in the process of attempting now, with our low radioactivity situation, to observe dark matter candidates. We know that that's not neutrinos, but dark matter, and we'll talk about that as well, influences the way in which the structures in our universe, such as stars, galaxies, particularly galaxies, and larger scale structure, right up to the largest of all the scales, how they formed, in particular our own galaxy, the Milky Way galaxy, and we'll talk a bit about that. But these particles, these dark matter particles, fit nowhere in anything else that we have observed so far with respect to the microscopic structure of matter. And so it's a very important topic, and it could be a real tremendous breakthrough if we are able to actually observe dark matter particles for the first time. We've pushed our sensitivity several, factors of more than 100 in the work we've done so far, and we have factors of about 1,000, to the point where, ironically, the thing that will limit us is neutrinos, which was our main objective in the first place. So why do we go underground? You can see here, that's quite a spectacular bit of northern lights, because you can still see it above the lights of Sudbury. That's the famous smokestack in Sudbury during a solar storm. The reason we go underground is to avoid this, because it is particles, astroparticles, that are bombarding our atmosphere that cause these glowing northern lights. And what we want to do is to measure the occasional event which produces a burst of light. And so doing that on the surface would be very difficult. And we go down by a factor of a million or so in terms of those particles being shielded out by the rock above us in the experiments that we do. So just to show you where it is or what it is we do as we go underground from the surface to our ultra-clean underground laboratory underground in SNOLAB now, and very similar to what it was in SNO. I'll just give you a little tour. We travel with the miners in an elevator, they call it the cage, which is 3 meters by 4 meters, roughly, 2 levels. You're standing like this, 44 people on each level. So let's take a little trip underground to the laboratory and you'll see what I mean. So we start with the miners. We go over to the cage and load up in the cage and start underground. The cage will travel eventually at about 50 kilometers an hour straight down. It's 4 CN towers that we're going down. You can see it happening here. It's amazingly smooth, the ride actually. And the air pressure goes up by 30% until you get deep underground, and eventually you come to the bottom of this shaft, 2 kilometers down. And then you have to walk some distance in the, what they call the drifts, or really the tunnels that get you to the mining areas, or in our case, to our laboratory. And you can see people walking along there. And then when you get there, you change your clothes, take a shower, change your clothes, put on clean, lint-free clothing. And then at that point, you're able to go out into the ultra-clean laboratory. And here, this is a early photo of the ultra-clean laboratory for SNOLAB, very similar to SNO. Right now, this has several experiments that I'll show you later that is occupying that space. So that's where we go. All of the equipment that is associated with the experiments also has to go in that same 3 meter by 4 meter mine cage to be transported down. And so it's an effort to try to make the experiments modular, let's say, in order to make them successful. Now, the topics that we can study once we get to this ultra-low radioactivity level are very fundamental. I mean, what's the composition of this universe? And how has it evolved to the present? We'll spend some time on that. What are the basic laws of physics for those very fundamental particles? How do stars like our sun burn and later become supernova? Because that turns out to be the source or the origin of a number of the elements from which we are composed. Carbon, nitrogen, oxygen are made in stars like our sun. And finally, the big puzzle we're working on these days, what is that dark matter that actually, when you look out on a starry night, there's 5 times as much mass in the dark spaces than there is in the glowing matter. And so it's a fundamental part of our local universe, even in our galaxy, and we want to know what it is. So let's start by talking about the elementary particles as far as we know them right now, going down to the smallest, the neutrinos that are thought to be smaller than 10 to the minus 18 meters in diameter, or in their influence zone, let's call it. But in addition to that, I mean, you probably certainly learned in school about atoms with in the nucleus, neutrons and protons, and around the nucleus, electrons, giving it its chemistry properties. But it turns out that it's now been discovered that there are quarks inside those neutrons and protons. Actually, it's a Canadian, Dick Taylor, who discovered this at Sanford Laboratory in California and got a Nobel Prize for it. It's a structure inside neutrons and protons. And these are the particles we don't know how to subdivide any further. And the components of our ordinary matter are up and down quarks, electron neutrinos, and electrons. The others are heavier versions of this, and they are observed in cosmic rays or in high-energy experiments. And there are components of the forces represented over here. Gravity is not yet in this theory. That's the theory of everything that people are looking for. But there's the photon from electromagnetic, there's the gluon from the strong force, and the Z and W for the weak force. And the combination of weak and electromagnetic is fairly well defined as well. Higgs boson gives mass to all of these particles in the standard model, except it also predicts that neutrinos have zero mass. And what we observed, in fact, is that they do have a finite mass. And so we have to add to this standard model, and that's really what the Nobel Prize was given for, a modification of our understanding at the most basic level. Now, neutrinos are unusual particles because they don't have an electric charge, they don't feel the strong interaction, and so they only feel the weak interaction. And so they are produced in radioactive decays or in the cores of stars like the sun through nuclear reactions. They are, however, very difficult to detect. Dark matter, on the other hand, as I said earlier, doesn't fit anywhere in this model. And so if we observe dark matter particles, it will be observing a completely new form of matter that presumably was produced in the Big Bang. We're looking for that. We know it's in our galaxy. It may also be possible to create it, and the highest energy accelerators in the world at CERN, Large Hadron Collider, are attempting to do just that. But we really don't know what it is yet. We're working hard at it. Neutrinos are very unusual particles, as I said. They only feel the weak force, very difficult to detect. You need a detector the size of a 10-story building to observe one an hour. That's what the Sudbury Neutrino Observatory was. But by observing them over a period of about 7 years, we collected enough of them to determine that, in fact, the electron neutrinos produced in the sun had changed their clothing to one of the other two types. The other two types we saw on the previous slide are mu neutrinos or tau neutrinos. Electron neutrinos are the only type that's produced in the core of the sun. There are many sources of neutrinos. This shows you the energy of the neutrinos, and these are very, if not impossible at this point, to detect. Very low energy produced in the original Big Bang. The most prolific of the others are the ones produced in the sun, as you can see here. So just to show you how weakly interacting they are, but how many of them there are, just hold out your thumbnail for a moment and count to 3. And during that time, there will be about 15 billion neutrinos have gone through your thumbnail. So they're enormously prolific. You have no idea that they're there. Perhaps once in your lifetime, a neutrino will hit one atom in your body and turn it into another type of atom, but you won't even be conscious of it. Well, perhaps if it happens to hit you in your eye, and if your eye happens to be closed, as many are by the time I get to this point in my talk usually, then you might see a little burst of light, and that's, in fact, the way we try to detect them as well, is through the burst of light they produce in our detectors. But it is these solar neutrinos that we study. There are also neutrinos produced in the atmosphere, typically muon neutrinos, produced in the atmosphere by cosmic rays interacting in the atmosphere. That's what the Super Kamiokande experiment used to make their measurements of neutrinos oscillating, and that's why we shared the Nobel Prize with them. So let's talk about the SNO project, or the Sudbury Neutrino Observatory. This is an actual picture of the SNO detector looking up from the bottom, and you'll see in a moment that there's a big central sphere of plexiglass or acrylic, and that's what you're seeing here. It was what was filled with 1,000 tons of heavy water, unusual, uniquely Canadian material, and it's looked at by 10,000 light sensors. It's deep. The Creighton mine, we've been very fortunate with Inco and now Vale to have very good relations, and they've allowed us to develop a site, in this case here. The yellow material is the ore body. I'm not sure if you know, but the reason why there are so many mines in Sudbury is that millions of years ago there was a major meteorite impact there. And this is sort of the forward fracture zone of the meteorite, and the nickel copper ores are getting richer and richer as you go down. We are in a stable location in granite rock 2 kilometers down, or about 4 CN towers down. It's ideal from our perspective, and it is the best location in the world for suppressing cosmic rays as a background, but we also keep the whole laboratory ultra clean, and that helps also in terms of local radioactivity control. So this is what we built. You can see that person is to scale. It's about the size of a 10-story building. There's this plexiglass sphere that had to be made, put together underground from about 120 pieces that were small enough to come down in that mine cage, surrounded by those 10,000 light sensors, and then that's surrounded by, this is about 1,000 tons, which we got on loan from the Canadian government for $1, which is not bad leverage in any market, I guess. And the lining was actually developed by the mining engineering department here in Kingston at Queen's in order to suppress, well, it's very watertight, but it also suppresses radon gas, and it was designed to spray on the walls of uranium mines to try to protect the miners from radon, which comes from the decay of uranium, so they could flow fresh air into the mine and not have much coming out of the walls. But for us, it was perfect, and we used it as our basis for water and radon suppression. So a neutrino comes in, produces a burst of light, and we see it in these 10,000 light sensors. Now, constructing it was a major process. You can see here this acrylic sphere that was made out of those 120 parts. You can see it at the various stages. This is when we were putting in the structure of the support for the light sensors. You can see that here. And you can also get a scale for it, because here's the people with these lint-free clothing who were involved in the construction. So what we're talking about is a couple of light nuclei coming together and fusing in the sun and producing electron neutrinos that penetrate through the solar system. This one happens to be heading exactly for our detector in Sudbury. It goes past our surface buildings and down into the mine, where it reaches our detector and produces a burst of light. And by having heavy water, we had a unique advantage in our measurements. Heavy water is something that you may have heard discussed in terms of Canadian nuclear reactor style, CANDU nuclear reactors. Basically, it's a non-radioactive material that has an extra neutron in the hydrogen nucleus. So instead of just having one proton, there's a proton and a neutron. The number of electrons remains at 1 going around it, because that's defined by the positive charge on the proton. And so the chemical properties are essentially the same between heavy water and ordinary water, although I'm not sure. Bill, did you know that it's not dangerous to drink heavy water at the time? Bill, back in the day when we were trying to convince people in Sudbury that this was all very benign, actually went to a council meeting and said, here's a container of heavy water, it's perfectly safe to drink. In fact, he brought along a container of scotch as well, and poured it out and said, nothing improves the flavor of scotch like a little bit of heavy water. And so he managed to convince them, fortunately, and we were then and thereafter billed as the lowest radioactivity place in the world, rather than something you should be afraid of. But this heavy water with the extra neutron, we were able to borrow it because of the reserves for the CANDU style nuclear reactor, where they use it to slow down neutrons to initiate the next emission of neutrons in the chain. It already has captured a neutron, and so capturing another one is much more difficult. And so the CANDU reactor can use natural uranium rather than having to have it enriched in order to run it. So it's a unique style of reactor. But we were able to borrow 1,000 tons of it, $300 million, $1 million a year in insurance, but otherwise. The extra neutron makes it possible to determine two different signals, one of which is very explicit to the type of neutrino that is produced in the sun, electron neutrinos, and the other is equally sensitive to all three neutrino types. And so if you look at the ratio of those two, if there's an equivalence, if all of the total number is matched by the number of electron neutrinos, then nothing has happened, basically. But what we ended up observing, as you'll see in a minute, is that only 1/3 of the neutrinos were still electron neutrinos by the time they got to our detector. That implies that neutrinos have changed from one type to another. That is outside what was predicted by the standard model, and also can only happen if neutrinos have a mass which is greater than 0, rest mass greater than 0. And that is then the fundamental piece of science that we measured. And so you can see here, we measured 1/3 electron neutrinos and 2/3 muon and tau that were captured in our detector, and that's what implies that the standard model has to be changed. The Super Kamiokande experiment used ordinary water to study neutrinos from the atmosphere, and that's what led to the Nobel Prize being awarded to Super Kamiokande and to myself, as I say, as a leader of this very capable team. Now, there are other things that you can learn besides that basic science. We were able to measure very accurately the neutrinos produced by the fusion reactions that are powering the sun. And they're held in place by gravity. And it's an extremely intense core of the sun and giving out an enormous amount of power, as you know, simply from the amount that gives you a sunburn here on Earth. But the hope is that one can harness similar fusion reactions in a container here on Earth, which isn't gravity, obviously. Instead, it's something that is confined, or the hot plasma that is millions of degrees, hot enough to burn any wall in a bottle. Instead, you make a magnetic bottle. It's called magnetic confinement fusion, and one of the most advanced version of this is the ITER, International Tokamak Experimental Reactor, being built in France. Canada's a part of that, in which you're trying to confine the sun in a magnetic bottle. Now, what we've been able to show is that the calculations that are accurate, very accurate for the sun, they are the similar calculations to what you're trying to do in order to do fusion power here on Earth. And that's a valuable validation in itself. But as I mentioned earlier, we come from the production of carbon, nitrogen, and oxygen in the sun in a series of nuclear reactions. And in fact, that's what Willie Fowler got a Nobel Prize for, as Tony mentioned earlier on. So Haboon Mack and I were students together there in Caltech. So we're going to talk about the Big Bang Theory, which is how the universe evolved. So not this Big Bang Theory. And I was actually honored to be the Geek of the Week at that Big Bang Theory. It turns out that the fellow who was the scientific advisor for the whole series was a student of ours at Princeton when I was there, worked for us in the summer. And so I got a chance to go and observe a filming. I didn't get in the program myself. I'm not Stephen Hawking, but I did get to observe how it's done. And my son Fraser and his wife, he's a film post-production specialist, actually films all the Queen's athletic games these days, was along with me as well. So it was great fun. But instead, I'm going to talk about the Big Bang Theory as we know it today. And it's quite a remarkable achievement. And in fact, it's an achievement that you heard a bit about this fall, because a lot of what went into understanding how the world has evolved since the Big Bang can be attributed to the work of Jim Peebles, another very proud Canadian from Winnipeg, who's worked for his whole career at Princeton University as a professor. And he received a Nobel Prize in 2019 for that work. And he explored concepts. He's very good at interacting with experimentalists and astronomers in terms of what has been observed, which get incorporated into this theory. So the thought these days, and we're always very careful to say this is what we think is correct, but scientists are very careful to say, I can only really believe something if it's been tested in an experiment. And right now, we can only test things that have happened since the Big Bang. We can't go back and see what happened before the Big Bang or even really close to the Big Bang. But we look as close as we can get. And the Big Bang, we think, happened 13.6 billion years ago. And at that point, an enormous amount of energy was deposited in a very localized spot. That energy got converted from from energy to equal amounts of matter and antimatter. Now, every particle that we know that's in that standard model I showed you earlier has an equivalent particle, which is its antiparticle. They've all been identified. The one you might be familiar with is the positron. The positron is the antiparticle to the electron. And so positron emission tomography, or PET scanning, is something you may be familiar with. How many have heard of a positron in that context? It's pretty well known these days. And in that case, you've got an electron in material, such as in your brain, being located by a positron that comes from radioactive decay of a radioactive substance that gets injected into your bloodstream. And when the positron finds the electron, it converts back to pure energy. But because they're at rest, that pure energy has to effectively be at rest as well, so it produces two back-to-back gamma rays. And the way in which the tomography works is you put an array of detectors around someone's head, for example, or other parts of the body, and you look for the lines that connect between the two detectors that fire off with the two gamma rays at the same time. And by using all of those lines, you can determine where the radioactivity that's been injected in someone's bloodstream gets to in the brain, and of course, also where it doesn't. And you can locate tumors. You can even use it to find out what part of your brain is active when you're listening to music. So it's a great technology. But that's the opposite of what happens in the original Big Bang. In the original Big Bang, you have this tremendous amount of energy that produces electrons, quarks, neutrinos, and their antiparticles. And those are produced in a very short period of time. There's an enormous inflation that takes place at that point of the universe. And then that expansion continues thereafter. And as it does, it cools off. And so those particles after, well, you can see the temperatures here, even after 10 to the minus 32 seconds, it's still at 10 to the 27 degrees Celsius. It gets down to only 10 to the 13th after about a microsecond. And at that point, the quarks can clump together and become neutrons and protons. After about 3 minutes, then they can clump together to make the nucleus of atoms. And after 300,000 years, electrons can be attached to make the elements that we're now familiar with. And then over the next, in this case, almost 13 billion years, you see the small fluctuations in density that exist at this time, producing eventually stars and galaxies and the universe as we know it today, 13.6 billion years. later. Now, you've heard a lot of hype about the James Webb Space Telescope recently, and one of the reasons for that is it's now capable of having a sensitivity that enables it to go back and look 10 to the 12th billion years. And so it's actually getting back to this period here where the early formation of galaxies and stars is happening. So the information that comes from that is very valuable in terms of going forward. Now, there's a lot of evidence that says that this seems to be what's happening, but there's still things that are unknown. One of them is if you had equal amounts of matter and antimatter produced in the original Big Bang, where's all the antimatter? You're not seeing pile of positrons up in the corner of the room producing gamma rays. Somehow the antimatter has all decayed away, and we're left with a matter-dominated universe. And one of the things that we're attempting to understand is what may have had the processes that enable that to take place. And the most popular theory, in fact, the only one that seems to work, is one that involves neutrinos. And one of the properties that we're looking for to see whether this theory may be valid, we can measure at a renovation of the SNO project called SNO+, and the other of the properties can be measured at major accelerators. In fact, it turns out that the Fermilab accelerator in Chicago, the highest energy in the United States, is essentially doing entirely neutrino physics these days. This particle astrophysics has become a very, very significant field. And I have to say the work that Tony has done with respect to the development of this institute they named after me, it should be named after Tony, for what he's done, is quite remarkable in terms of enabling Canada to get into the game of this rapidly expanding field of astroparticle physics. Tony has connections with 7 universities across the country, tremendous amount of outreach, activities happening here and elsewhere, and support for the sort of major experiments that I'm going to be talking about in the next while. And so I have to say thank you to Tony publicly for all the work that he has been and is continuing to do with respect to this McDonald Institute. But if we look at SNO+, basically what's been done is to put in the central acrylic sphere a so-called liquid scintillator, which puts out about 50 times more light than heavy water did back in the previous days, providing opportunities also to look at the neutrinos coming from the Earth. Turns out that liquid scintillator is lighter than the surrounding water, and so you have to hold it down instead of holding it up for the heavy water. And the plan is to put in next year about 4 tons of a material that is called tellurium, that is a very good candidate for this process of emitting 2 electrons and no neutrinos in the process of a very rare radioactive decay. Lifetime in the excess of 10 to the 26 years or so. But if you remember that Avogadro's number says that in a molecular weight of material, there's 10 to the 23rd atoms. By the time you get up to 4 tons of this material, you've got quite a number of atoms there to start looking. This is a shot inside the detector showing you the liquid scintillator is lighter than the water, and it floats on top, and that's in the process of installing it. The other question that's to be addressed by in this question of whether neutrinos are responsible for the decay of matter and of antimatter in the early universe is to be answered by accelerator experiments where the Fermilab, as you see at the bottom, Fermilab accelerator in Chicago is shooting a beam 1,300 kilometers to an underground location in South Dakota. And in Japan, the most powerful accelerator near Tokyo is shooting across Japan to a very large detector, 10 times the size of the Super Kamiokande detector I showed you. What they're looking for is whether there's a difference in the oscillation whether you start with muon neutrinos or muon antineutrinos. And that can tell us whether that is part of the puzzle as to what happened to all the antimatter. So Canada, by having the lowest radioactivity location in the world, and in fact, a place that the world is wanting to come and participate. I mean, there's a $50 million experiment being installed right now, mainly supported from the US, and there are others in the future of 4 or 5 times as expensive as that, potentially also paid very largely from offshore. Because it is the lowest radioactivity location, and because you need these enormous experiments in order to be able to compete. But people want to come to Canada to our laboratory, and we're very fortunate, and very fortunate also with the institute that Tony has developed to have the scientists that are capable of working on these experiments, including many who are here at Queen's. So we're in the game worldwide, and you can see it's a big game. Both of these accelerator labs are dominated by work on neutrinos. So let's go back to the Big Bang Theory for a moment and talk about the other topic, which is what is the dark matter that makes up 5 times as much mass as the glowing matter? Because we know from Jim Peebles' calculations that it strongly influences the way in which the universe has evolved. We know it's here because, you know, when you look at the Milky Way, you see it as a band of stars in the sky, but it's actually more like a cinnamon roll if you look at it side on. And you're looking along the plane of the cinnamon roll. Now, these stars in the outer reaches of this spiral formation are traveling so fast that they would have long ago spun off into space if there wasn't 5 times as much mass in the dark spaces as there is in the glowing spaces. And so we know that it's there gravitationally. This is a plot of the velocities as a function of distance out from the center. And it should look like this if there isn't any additional matter, but it actually looks like this, implying there's a substantial amount of dark matter. It turns out also that if you look at the universe at a distance, you can determine the mass that is between a glowing object and you by looking at the way that glowing object image has been distorted by general relativity, prediction of Einstein's, that light gets bent by mass in the intervening region. And so it's possible to interpret how much mass there is in the universes in general that isn't glowing compared to the glowing, and you find the same thing, about 5 times as much as the glowing matter. In addition to this, this is a rather unique and beautiful picture of the fact that these are clusters of galaxies that have moved through each other. They've collided. The red or the pink is X-ray information, which comes from the emission from ordinary matter. The blue is inferred from that gravitational lensing process of seeing how the images behind are distorted. And what you see is that the 2 blue blobs have moved straight through with very little impediment, whereas the pink has been slowed down by the interaction. And so what one concludes is what you're dealing with is weakly interacting massive particles, or WIMPs. We have fun with such names in physics, and in fact, if you go over to Sterling Hall and go into one of the research areas, you'll see that one of the student groups has put a sign on the window of their research area that refers to themselves as nerds searching for WIMPs. So, as I say, we love these sorts of terminologies. Now, the other thing that's been really fascinating in terms of confirming this model is the fact that you can look at the light that penetrates through once the electrons find the atoms about 300,000 years after the original Big Bang. It's cooled off at that point to about 2.7 degrees above absolute zero, about minus 270 Celsius. It's called the cosmic microwave background radiation. It's microwaves, and in fact, if any of you can remember having a TV set and an antenna some of the snow on Channel 3 actually came from that. So it's definitely there, but now it's been measured in an exquisite way. It turns out that if you look at the entire sky, the variations in intensity of this 2.7 degree radiation, it's only about a part in 10 to the fifth that it varies. But if you look carefully at the intensity of these different spots versus their size, I mean, these are technical plots, but basically what you're looking at is the distribution of this light as a result of how the universe looked 300,000 years after the Big Bang. It turns out, if you look at you can see maybe some little blue dots in there. The averages of them are these red points. And the blue line is a theory based on this theory of how the universe has evolved, with only 6 parameters in it. 3 of them being the amount of matter, the amount of dark matter, and the amount of something else called dark energy. And in fact, from that beautiful fit, you can infer that the composition of our universe is about 26% dark matter, only about 4% ordinary matter like us. I mean, this is sort of like Copernicus when he said the Earth is no longer the center of the world, it goes around the sun. This revolution in the last 60 years or so in saying that we as matter-based objects are a very small fraction of the entire universe. The dark energy is another concept which relates to what Einstein had in his theory. Basically, what's been discovered is that what you learned in high school, university, that gravity is an attractive force between 2 masses, is not totally true on very large scales. There's a small repulsive force that has resulted in the acceleration of the universe. They look at supernova, which are very well calibrated in the amount of light they give out, and they can tell how far away they are just by the amount of light you receive, and they can tell how fast they're moving. And that was enough to prove that, in fact, the universe has been expanding. That can be expressed as an energy field, and it makes up the other 70%. Now, WIMPs. It's one model for what that dark matter in our galaxy could be. There are other models, and they're some of them quite fanciful, but the main models are 2 or 3 of them, and this is a primary one among them. The idea is that these are weakly interacting massive particles. Weakly interacting, they can penetrate through the rock above us and get to our detectors, just as neutrinos did. And so we have a series of detectors in the SNOLAB facility that use different materials presented in a low radioactivity location so that you can exclude other forms of production of a signal other than the signal that you expect from a WIMP coming in, hitting a nucleus, and making it recoil. And we have a number of those experiments. Whoops, there. What's happening? Oh, I'm pressing the on-off rather than the move forward. This is what SNOLAB looks like. This new area in red is what has been excavated on the same level as snow, ultra clean everywhere as we had in snow, and many experiments, international collaborations from Canada and around the world. You'll notice that the ones labeled dark matter, I've also labeled the particular material that they're studying. In this case, argon, helium, neon, fluorine, silicon, germanium, again, fluorine here. We're presenting different materials to see whether there are interactions with dark matter particles with suppression of background to the point that you could see a couple of interactions from WIMPs per year and get rid of all the other radioactivity effects. And the facilities themselves are rather beautiful. They're kept in this ultra-clean situation, class 2000 for those technically minded. This on the right is a picture of the cavity that has not yet been filled. It's one of these major experiments that have indicated they would like to be sited there, and that's in process of determining the funding. This is back in 2012 when Stephen Hawking visited for the second time. You can see he's there in the midst of all of our students and staff and so on. An absolutely inspiring individual. Most inspiring when you realize that all of the really important work that he's done was done after he developed ALS, after he got his disability. And he has a completely different way of dealing with science than others do, but he made substantial contributions. At the time he visited this time, which he insisted on doing, we had invited him, he was going to come, and then he got pneumonia. When he got over pneumonia, he said, "Can I still come now?" And he came, and we took him underground in a special mine car that Inco originally had produced, so we could vacuum him off above ground, and he didn't have to take a shower. And but a sense of humor. After all these years of what he's had to put up with, he's great sense of humor. He was referring to this 2.7 degree cosmic microwave background radiation, and he said it's really cold, almost as cold as Sudbury in the wintertime. But the spirit of the individual and his intellect was really a wonderful thing. Here are some examples of the approaches that are being taken to the experiments. In fact, and there are certainly people from Queen's actively involved in these. This is the PICO experiment. It's one that's led actually by Tony Noble. And it has a unique way of using bubbles created in a superheated liquid by the recoil of that WIMP hitting a nucleus, which triggers a bubble. Turns out that the radioactivity, gammas and betas, do not do that, and so you've got a strong discriminating factor. And that has using fluorine has the best limit in the world for searching for dark matter that would interact by what we call a spin-dependent interaction. Super CDMS is that $50 million experiment that's being installed right now. It uses silicon and germanium crystals, ironically cooled to even more, even closer to absolute zero than that 2.7. And it measures a very tiny temperature rise as well as the production of electrons in the material. And the ratio of those two things is very different for background and for WIMP signals. And then finally, NUSG, which is also led in Canada by Guillaume Giroux in our physics department, is a very low radioactivity detector with great sensitivity that can work with very low mass materials like helium and neon. And that lead shield that is there is altogether 37 tons that had to be brought down by the mine elevator. And here's another one that a group of us here at Queen's, I'm actually involved in this one, has been working on for a number of years. Deep 3600 it's called. It's about 3 tons of liquid argon. Liquid argon has one of these properties that enables you to distinguish against or discriminate against background as well, because if a WIMP causes a nuclear recoil, you get a signal in about 10 nanoseconds, 10 to the minus 9 seconds. If you have radioactivity from gammas or betas, it takes 10 to the 6th, 10 to the minus 6 microseconds, in other words, a microsecond, 10 microseconds, something like that, 10 times 10 to the minus 6 seconds. So they're much longer signals, and we can discriminate against them to factors of greater than 100 million. But I don't expect you to read the things on the right. I just wanted to show you the complexity of these experiments. They're all typically of this nature where you have to have many, many parts that are kept at ultra clean conditions in order to do the experiment. That is the first step in a series of experiments of larger and larger size. All of the people working on liquid argon as a dark matter detector, in this case 400 scientists from 14 countries, are pooling their talents. The next thing we're building is a detector in Gran Sasso in Italy, and it'll be 20 tons. And the objective eventually is 300 tons back here in SNOLAB, because at that point, the depth that we need is essentially only obtainable in an easy way at SNOLAB. The other alternative would be China, which is a much more difficult place to work these days. That detector is built from using technology that was developed for the DUNE experiment, that experiment at Fermilab, developed at CERN actually. And what CERN is attempting to do is to make dark matter for the first time since the Big Bang by having enough energy in colliding beams to perhaps produce these dark matter particles, enough to have that energy converted into mass, just as it was back in the Big Bang. This is what the overall dark side 20K experiment will look like in Italy, and there's an interesting additional technology we've had to develop. It turns out that the argon produced in the atmosphere has trace amounts of radioactivity. The isotope is argon-39. But if you go deep underground, for example, in a CO2 stream that's taken from the ground in Colorado and used to pressurize oil wells in Texas and extract the argon from it, it's 1,400 times or more lower in that radioactivity. And so we're extracting it from the ground to the tune of 120 tons or so, and shipping it to a purification location in Sardinia, where we have a distillation column the size of the Eiffel Tower in an abandoned coal mine. We're also measuring it very carefully in Spain, and it'll be installed in Italy. So you can understand the international nature of this research, and that 400-member collaboration is committed also to coming to SNOLAB next. And when we continue to extract argon from underground, we'll be storing it at SNOLAB. Finally, I just want to point out that fundamental science is not only valuable for its own purposes. I mean, these are existential questions that I've been talking about, not just where did we come from as humans, but where did everything come from? All of the things you see in your world, how did they originate? But in addition to studying that, we also have to push technology to its limits. And I thought Time magazine was very perceptive in choosing Albert Einstein as the person of the 20th century, because Einstein, didn't invent the laser or the computer or the GPS or other parts of the technological revolution that characterized the 20th century. Turns out that the last meter or so on your GPS requires general relativity in order to get that sort of accuracy. But because his insights in fundamental science led to all of the technological revolution that occurred in that century. And we try to be very conscious of the new technology that we are developing for our purposes being of value in other ways. In the case of liquid argon, the use of liquid argon, but also the use of new types of light sensors called silicon photomultipliers, is now being in a development project to try to reduce the amount of radioactivity you have to put into a person's arm in order to use a PET scanner for them. And the hope is to be able to reduce the age at which you can start treating people, because if you give too much radiation to young people, it's not regarded as a safe thing to do. And then at the beginning of COVID, there was a call for more ventilators. Someone in the ICU with a severe form of COVID at that point had a 50-50 chance of surviving if they didn't manage to get on a ventilator. And so we repurposed ourselves from that collaboration with a lot of help from places across Canada like Chalk River, SNOLAB, Triumph Laboratory, and of course also from people at the McDonald Institute, and developed a new kind of ventilator that has many fewer parts, 50 rather than 1,500, and more easily sourced, and supplied a number to the government for the stockpile needed to deal with such things. So, in summary, understanding the universe from a hole in the ground. Well, the hole in the ground seems to be very valuable, and there's been enormous progress in the last year, and not only the hole in the ground, but also last 60 years, not only the hole in the ground, but also the work that's been done in astronomy from satellites. But measurements of neutrinos and dark matter can make major contributions to progress in understanding our universe as a whole and its evolution. Canada is a leading country with SNOLAB, and also leading with respect to what Tony has created in terms of the scientific capability to do these experiments. And so we're very hopeful that we can continue that sort of leadership and push the frontiers of this fundamental and even existential area of study. And in the process, we're driving technological innovation, but we're also training a next generation of students who are not only valuable for doing basic science, but the 75% of our graduates, we did a survey from the SNO project, end up in a wide variety of other roles in society. And I think the thing that unifies them is that they've been taught evidence-based decision-making, which you have to apply when you're doing science. So, okay, that's the end of the talk as it stands. And as I said earlier, this is rather complex, and you may not have really caught everything I said, but at the time of the award of the Nobel Prize, this hour has 22 minutes, took note of the fact that I was struggling a bit in the interviews, and so they have a take on what I just said, which perhaps might resonate with some of you. I'll play the script that they wrote that I was asked to recite, and we'll see if it maybe has a bit of a ring, particularly for a Canadian audience. So remember, these are Newfoundlanders writing this, and I'm from Cape Breton. So maybe that'll help you understand what she says at the beginning.
It's an illustrious list, including Lester B. Pearson, Alice Munro, and now a guy from Cape Breton. Physicist Arthur McDonald is Canada's latest winner of a Nobel Prize. Here to explain why he's the best in the world at what he does is Art McDonald.
Hi, I'm Art McDonald. I'm a professor emeritus at Queen's University, originally from Cape Breton, and I attended Dalhousie University. And I'm a co-winner of the 2015 Nobel Prize in Physics. People from 22 Minutes have asked me to come in and explain what I and our team did to win this prize. We demonstrated that the flavor of neutrinos produced in the core of the sun, electron neutrinos, changed into one of the other two flavors, muon and tau neutrinos, as they traveled from the core of the sun to, okay, I'm being told I have to make it simpler. Neutrinos are very basic subatomic particles that we don't know how to subdivide any further. And okay, they're asking me to dumb it down a little bit. A subatomic particle is smaller than an atom. Atom is a unit of matter. Really? You don't know what matter is? It's seven. Okay, neutrinos are like Timbits. Chocolate, sometimes they're like cherry filled, and sometimes they're like the old-fashioned glaze. I must be the first person that ever won a Nobel Prize in Timbit.
So you have to be very careful when you refer to something as having different flavors. People are going to take you pretty literally in some cases. Tony.
Okay, well, thank you very much, Art. That was absolutely fabulous. I'm always so impressed when I, even though I'm in the field, when I see how connected and how international and how difficult these experiments are, and knowing that the young people that we're interacting with today are getting involved and are really driving a lot of these experiments, it's such a wonderful feeling. So we're going to have some opportunity for some Q&A, and maybe I'll get some chairs because you've been standing for. There you go. Can't actually see very well.
There's a microphone there.
Yeah, I'll grab that. Am I live? Can you hear me? Yep, okay, great. So, yeah, it's a wonderful opportunity. I certainly invite people from the audience. There are some runners around. I see Mark and Alex over there. So if anyone has a question, you'll have to help me find you. But it's really an opportunity. Don't be shy. Do you see any questions yet? Oh, there's one there in the middle, of course. So what we're going to do is everybody gets a chance to ask a question. Well, maybe not everybody, but we've found in the past that it's very difficult to have multiple questions from a single person. So once you've asked your question, hand the mic back and we'll move on to the next person. But please go ahead.
How hard was it to convince the Canadian government to dig a two-hole hole in the ground?
Do you mean
Somebody had to pay for it.
Do you mean back in the early days of snow? Well, there are two answers, one relating to snow and one relating to SNOLAB. In the early days of snow, that's a role that George Ewan and Bill McClatchy and others played a very strong role in, because at that point what we were asking for, which was in excess of $50 million, was way beyond the scale of anything that any ordinary funding agency could consider. But we did get very strong peer reviews and everything that we put forward. And we ended up with a significant 25% from the US and 5% from the UK that had larger structures for approval according to straightforward peer review. So it took a lot of convincing by a lot of people at the various levels of government for this to take place. But it was a one-off at the time. By the time we came to 2002 or so, David Sinclair, who was George Ewan's first graduate student and who you saw in that original picture, he was the original UK spokesman, put forward a very well-developed request to something that the Canada Foundation for Innovation had put on the table. They said, we want to build 3 or so laboratories in Canada, and here's $100 million that will be devoted to that. And David wrote a wonderful proposal and also then developed, did the construction and developed the SNOLAB, and then Tony took over actually as the first director of the SNOLAB as it was going into operation. So by that point, we were at a stage where the government had recognized that having international laboratories that attract people from around the world to come and work with Canadians in things where Canada has a natural advantage was a good thing to do. And so it was, the way we like to do it is by peer review wherever we possibly can. And that's what happened for SNOLAB. The others, by the way, were Ocean Networks, which has built an underwater network off Vancouver, and the Amundsen Icebreaker, which does research in the north.
One down? No, okay.
I don't think this, oh, it's on. I'll take questions as they're available too.
A very short anecdote and then a question. A couple of years ago, I pulled into the Canadian Tire parking lot up here at Bath Road, and the car in front of me said, on the license plate, said Neutrino. And I thought, that can only be one person. And I walked up to your window and I knocked on the window, you rolled it down, and I said, you won a Nobel Prize. And you said immediately it was a team effort. And I just thought that was a really classy response. So the question is, what comes after the standard model of particle physics? If we cannot generate the energies to nail down dark energy, what does that mean for the standard model, and what comes next? Thank you.
Well, there are several answers to that. Dark energy and dark matter are very different in their nature and are studied in very different ways. Studies of those supernova with ever more sensitive satellite-borne instruments is what's happening in terms of trying to understand dark energy in terms of its influence in this straightforward way of accelerating gravity. Dark matter, we have pushed the sensitivity for weakly interacting massive particles, as I said, by factors of more than 100. We have more than 1,000 to go. And at that point, we're going to be very limited by the fact that neutrinos are going to behave very similarly in our detectors to what dark matter does. And that's the level at which they will start to interfere. There are many other ideas for what dark matter might be composed of, and many other types of experiments that are being applied to explore those ideas. But basically, it's sorry, you're looking in the dark here. I mean, you really don't know what you're looking for, and you don't know how strongly it might interact with ordinary matter. There are lots of theories that predict various things, but they're just predictions until they've been observed experimentally. But that's the fun. I mean, I hope you've got the sense that what I think is that doing science is really fun. And I'm just hoping there'll be next generation of people that are inspired by these existential questions and willing to devote time to getting the best new technology to try to push things even farther than now. And that's about all I can say to you. Keep looking.
Question down here, Alex. Could I take a question up here while Alex is navigating?
The James Webb Space Telescope is making some fascinating observations, especially ones way out near the Big Bang, 300 million years after the Big Bang. Things like black holes that are much, much more massive than they should have been because they didn't have time to form so quickly. Same thing for galaxies and clusters of galaxies. They're much, much bigger than, technically, according to all these current theories, didn't have time to form. Do you think James Webb is going to really shake things up and we got to reconsider even whether the Big Bang is like we think it is?
Well, I can't tell because it depends on what they see. And I'm not an astronomer to be totally up on the new things that are being observed. Black holes are somewhat independent of the overall thrust of the evolution of the universe, although they are related. But the question of the role of dark matter, for example, in the formation of galaxies, which are forming at that time, 1 billion years after the Big Bang, it'd be very interesting if they find microscopically when they look at those early galaxies that the influence of dark matter is different than what has been calculated so far for the generality of the data that we've known so far. Perhaps there's things to be learned there. So it's difficult to speculate exactly what will be found and what influence it will have. But, I mean, clearly from what I said, we're fine-tuning all the time our knowledge of this. Whether it overturns the whole thing, you just have to wait and see. So, but it's wonderful to have instruments that go back that far. And very interestingly, the daughter of Herb Chen, the individual I mentioned as the original US spokesman, who was a wonderful scientist and who actually passed away about a year after that picture in his mid-40s from leukemia that showed up shortly after that picture was taken. His daughter is a principal scientist on the James Webb Space Telescope. So when I say I'm hopeful that the next generation will take over, here's a very prime example.
Tony?
Yeah, go for it. I can't see you. There's a
Hello.
few questions down here as well in a moment.
My question was, you mentioned that the mu and tau version of things are generally heavier than the electron version of things. So if neutrinos are changing flavor as they're coming from the sun, is the idea that they're also gaining and losing mass as they're traveling from the sun?
I didn't quite catch the question.
So the question was if the neutrinos have different masses, does that mean they are somehow gaining or losing mass as they traverse from the sun?
No, they are not. It's a quantum mechanical effect, which, well, it's very difficult to explain without going into the language of quantum mechanics, but it turns out the three states that are formed, which look like an electron neutrino, a muon neutrino, and a tau neutrino, if you were to observe them immediately after they were formed, are thought to be composed of different combinations of states that look like mass 1, mass 2, and mass 3. They're combinations of them. Quantum mechanically, as they travel, the phases between those states can change, so that when you make a measurement of how much of what you're observing looks like the original thing you started out with, in the case of an electron neutrino, you find it doesn't look like that anymore. It looks some of the time like an electron neutrino, some of the time like a muon or tau neutrino. And it's a fundamentally quantum mechanical effect where you deal with what you can measure in terms of probabilities, and it doesn't involve any change in effective mass of an electron neutrino, which is actually a combination of the three masses. So, sorry for such a complex answer. There isn't another that we know of right now. It was a good question.
It's a lot now, Tony. They're warming up.
Warming up. All right, good. We'll see how much stamina we have.
Dr. McDonald, you talked about the next generation. Now you've had some time to exercise some hindsight. What is a thing you might have done differently if you had the knowledge you have today in your past? Some advice for that next generation.
The advice I usually give to students if I'm in a session with them, as I think I'm going to be tomorrow, the next day, here at Queen's, two things. One, be curious, and two, be nice. Be curious is very important. You have to keep being interested in what you're doing, but also being interested in how your subject is changing with time. What are the fundamental things that you need to be, or you might wish to be, concerned about? How is the technology changing? Is that new thing that's been developed something that might give you an opportunity to make a measurement that, might answer some of these questions? But the other thing is, as I found, the be nice aspect of it, and I'm not sure everybody thinks I was, but that enables you to get so much more done if you've got colleagues like Tony and the others I mentioned here in the various projects that we've been working on. You can get so much more done in a collaborative way, locally, nationally, internationally, than you can as an individual. That if you take that attitude and remember that what you're doing is supposed to be fun, and it can be. That's the sort of simple advice that I usually give to young people these days.
I have a question up here.
Hello. This might be a little bit tangential, but I'm just curious, with having such a clean laboratory space so far underground, if different fields of study have been able to kind of take advantage of that environment, so like biological sciences. And I would regret not asking this question, but I'm curious if you know of my grandfather, Cyrus McClatchy, who's also a physicist from Nova Scotia.
Well, perhaps my friend Bill would know. Go ahead.
I met Cyrus McClatchy in an elevator about 25 years ago. And we were the only people in the elevator. This was in Dalhousie, and I just arrived for a CAP conference. I was just standing in the elevator, and I reached out my hand and I said, "Hi, Bill McClatchy," and he said, "Cy McClatchy." And that had never happened to us before.
Thank you, Bill. We have experts on everything here. But seriously, in terms of biology, there are several biological experiments that are taking place in the SNOLAB, but they're not so much concerned about the cleanliness. I mean, you can achieve that cleanliness, on the surface of the Earth, and that's done fairly routinely. But rather, they're concerned about whether radiation has an effect on biological processes. And so there's one of them I know is referred to as, well, the title of it is repair. And so it's looking for, I believe, the way in which biological objects that have had some damage from radioactivity can repair themselves by being in a location that has no radioactivity, relatively speaking. So 2 different types of experiments being done. And I'm sorry, I don't know the details of the other one, but certainly it's being used as a laboratory for that. The other thing that people are involved in and plan to do more of is studying the ways in which radioactivity can affect computer circuits, and particularly things like quantum computing circuits, where things induced by radioactivity can cause noise or cause errors, and so there's measurements being made of that in a completely different area. So.
Yeah, just to say, one of the other experiments studies the impact of working in a very different pressure environment deep underground. You feel really tired when you're underground. And so they have flies on treadmills doing exercises deep underground to measure their metabolic rates and so on. So there's interesting things that happen.
And there's a lot of innovation in the design of treadmills for flies, too.
Not really. You basically put a test tube on a hot dog roller and it just rolls. Maybe we should move on to some sensible questions.
It was sensible till I spoke.
Dr. McDonald, you talked about heavy water as being a uniquely Canadian material. I know it has to do with the use of CANDU reactors here in part. Can you elaborate a little bit on Canada's contribution to the production or use of heavy water?
I'm sorry, you'll have to repeat it for me.
The question was on the heavy water, and that Canada was a unique supplier of heavy water, and if you could say a little bit more about why that was.
Well, the reason why Canada chose to use heavy water in their reactors is that with heavy water, you can use natural uranium. You don't have to do enrichment. And if you're not planning to enrich uranium in order to make bombs, then, which Canada never was, then coming up with a reactor that only needs natural uranium is a real valuable thing to do. There's a long history of the production of heavy water in Canada in various locations. Ironically, my first summer job in 1963 was working in a steam power plant in Glace Bay, Nova Scotia, which ultimately became the source of steam power for the extraction of heavy water from the ocean near Glace Bay in a heavy water plant back then, in subsequent years. It was produced there. It's produced most extensively near the Bruce reactors on the Bruce Peninsula. But these days, there's a whole section at Chalk River, which is referred to as the Hydrogen Laboratory, which works on innovative ways to produce deuterium materials, partly for standard CANDU style nuclear reactors as heavy water, but also as fuel for fusion power, because the fusion power starts typically with deuterium and tritium, which is another isotope they work on in the so-called Hydrogen Laboratory. It's just another neutron. It turns out that is produced in Canada, is one of the biggest suppliers of tritium in the world, because once you have heavy water in a reactor and it does capture a neutron in addition to the two that are in deuterium in the first place, you get tritium. And it's going to be a fuel for the future. Not necessarily the basic fuel for a DT reaction in a fusion reactor, because tritium can be regenerated in the material surrounding the fusion power reactor. It's really the deuterium that is the fuel. And as I said, 1 in 6,000 of the molecules that you drink is heavy water. And so we have an unlimited source of fuel for fusion power if we can get it to work with hot plasma not hitting the walls. And that's the main objective these days.
Okay, I think we'll try and take a few more, but how's your stamina holding out?
I'm fine.
Okay. Down here?
I have a middle, and then I can come down here.
Okay.
Is that fine? In the center there, please, and thanks.
You mentioned Chalk River a few times. Was that a large gathering for people who worked on SNOLAB and developing projects?
So the question was, Chalk River, was that a gathering place for people working on snow?
It was to some degree. In the early days, the engineering team that came up with the original design for the snow project were working at Chalk River. And we actually thought perhaps that Chalk River would be the place where we were able to build a engineering team for the longer term, but it turned out not to be the case. On the other hand, the work that was done there and done by certain very key individuals who were continued to be leaders in the project, like Davis Earle at Chalk River, was key to our success. As it turns out, we went to a major engineering company that actually, the people that worked on snow had just finished building a reactor in Korea before they came to work for us. And not Chalk River, but Chalk River has played a significant role over the years, and we still have some people from Chalk River working on experiments at SNOLAB. So Chalk River, from my opinion, is actually really being rejuvenated. There's been a substantial amount of investment by the federal government in the last 5 years in Chalk River, because it's recognized that nuclear power is likely to be a very significant part of the energy mix going forward. There are many opinions of it, but as far as I'm concerned, it's a very clean source of power compared to, at least it produces no carbon compounds. And the existing reactors will have to be refurbished. There will be new ones built. And so the government has taken a perspective that Chalk River is a needed laboratory for future, and they've been supporting it appropriately. So it's a rejuvenated laboratory over the last 5 or 6 years.
Yeah, right here. I might point out the chief engineer for the entire project seems to be sitting over here.
Where? Hey. Wonderful to see you.
Please.
Professor McDonald, thank you for the talk. It was wonderful. You talked about the evolution of the universe starting from Big Bang, and I was wondering if science says anything about how this is all going to end.
Science says anything about?
How the universe is going to end. Something the opposite of Big Bang? Is it going to all collapse?
Well, by the way, the individual who did the original design at Chalk River and went on to be a chief engineer at SNOLAB for many years is Ken McFarlane, who I'm very pleased to see. I haven't seen you for a few years, and it's very nice to see you again. The current theory, which also is the one I was talking about, suggests that the universe is what they call flat, which means that the expansion will essentially coast, will continue and will coast to a cold ending billions and billions of years from now, but not result in a big crunch where it all comes back in on itself in the future. And so, well, for billions of years, we can expect the expansion that we now see to continue according to the theory that we have.
I have a question. You ready for this?
No.
Okay. As you mentioned on your slide, 4% of the universe is what we observe, visible matter, and I think the energy too that we know about, and 96% isn't. And I wonder, that's amazing that that's been found, but I wonder what interaction there is between the part we don't know about and the part we do here, like every day and in our atmosphere. And I realize that the way I hear it described, it's like the architecture of the universe and the energy that drives the universe to expansion. But I wonder you're finding dark matter at SNOLAB, so obviously it's coming here. What interaction does it have with a chemistry of something like climate change or our atmosphere, things that people might be missing? That's my question.
Well, we find that the measurements that have been made to date have not found dark matter, and by and large, those measurements are direct interaction with ordinary matter. And so it's, the sensitivity is such that dark matter interacts 10,000 times less than even neutrinos do. So there's relatively little, when I talk about neutrinos only occasionally interacting in your bodies, dark matter is negligible in comparison. And on the other hand, dark matter has a substantial influence on astronomical objects. And so you can't say it has no influence on ordinary matter, except the only thing we know about is its gravitational effects, which all happen on a large scale and for very massive objects. One of the things we're trying to determine is exactly what you asked about in terms of interacting with our normal matter-dominated world. So that's about all we can say. Dark energy, on the other hand, it's a different sort of process where it's an underlying nature of this universe. When it's expressed as dark energy, that's a field, as it's called, a field of influence on other things, such as the gravitational field interacts with other things, and it modifies that. And it's really only observable, as near as we can tell, on very large scale and very large distances. So in terms of interaction in daily life, it seems as though it's not likely to be substantial. I think that's what we know so far.
There's quite a few questions over here. Okay. If we can get the microphone down there.
Do you think that the Big Bang has a serious error in it? For example, when they pretend that the existence of the universe started with the start of the Hubble expansion?
Repeat it for me.
Do you think that the Big Bang theory has a serious error in it, in the sense that the expansion started when it did?
I'm asking if you think that the Big Bang has errors in it.
Well, right now, let's say we don't know of such errors. This is the theory that seems to work the best in terms of explaining all of the information, and there's a tremendous amount more than what I showed today. There are alternative theories for things like gravity, which would affect, of course, what the influence of dark matter would be, or even whether there is dark matter. Modified Newtonian gravity is one of the theories that's been put forward, but by and large, when these theories are tested, they fail in one way or another. And so the information I provided to you today is the information that appears to be fairly solid. And, but it's in a, you know, we're only as, in terms of theories, we're only as happy with the theories that we see in front of us as to the degree that they are tested. And I think if you heard Jim Peebles talk in the fall, he pointed out that, you know, in the 1960s, when he first started working on it, Big Bang was by no means the accepted theory. And in fact, it took a while for Einstein to come around to the Big Bang. At that point, there could have been other possibilities. But the one that got worked out over the longest period of time, and the one that Jim got a Nobel Prize for, is the theory that I presented to you today. So many things are put forward. Nothing else seems to have the completeness that what I presented does.
I think Alex will take one more question. Maybe you here. Yeah. And then we'll wrap things up. Sorry, I see there's quite a few hands, but we can't get to everybody.
First of all, sir, it's an honor to see you in person. And my question may sound a bit silly. So as you mentioned in your presentation, like the presence of dark matter, it affects the light, like from farther galaxies, it may seem different than what it should be. Does that mean that dark matter interacts with gravity? And also, as you mentioned, like as we can add gravity, maybe we can add gravity in standard model using the theory of everything. So in case, if we add like a particle, say graviton, in our standard model, would that affect in any way with the discovery of dark matter?
So there's a lot in your question.
I know, I'm really sorry.
So first of all, the process I referred to in terms of what's called gravitational lensing is something that Einstein's theory predicts. That is, anything that exhibits gravitational effect by having a finite mass can result in lensing of the light. And it's simply, from Einstein's theory, it's a distortion of space due to the presence of that mass that results in the straight line that would have been there for that light now being curved. And so that's independent of, as you put it, how dark matter interacts with gravity. It's simply the fact that it has mass. What was the remainder of the question? I'm sorry.
The second question was like, if we say like we add a graviton particle that describe the effect of gravity in standard model, would that?
Oh, yes. The theory of everything I put up there as what people are working towards in order to incorporate gravity into the standard model along with what works. And for example, string theory is one attempt to do that. There are a number of attempts to come up with grand unified models, as they're called. The difficulty is that none of them have really been proven to be correct so far, and it's very difficult to do so because quantum mechanics works at a microscopic level for tiny things, you know, smaller than the size of an atom. Gravity really only has its substantial influence on the very large scale. And so one of the only places that the two come together, in fact, is in black holes. And attempting to, one of the few successes for string theory in terms of showing that it might have some validity has been in attempting to explain the properties of what happens in the vicinity of a black hole. But there are other explanations as well. So far it's been unsuccessful. It's a quest. Okay, but the young lady sitting just over has had her hand up extensively, I know.
That's where I had
not cut it off.
Intended to end. Go ahead.
Hi, thank you. I just wanted to ask about the pie chart you showed before with the proportions of regular matter we see and dark matter and dark energy. And I wanted to know if those relative proportions were changing and if there was any implications of this, like if dark energy was increasing and one of the others was decreasing.
So again, I'm going to ask my friend who has working ears. But my wife claims that my problem is I don't understand women, and it's really true. My hearing loss is such that it's hard to please.
The question was whether the relative proportions of baryonic matter, dark matter, and dark energy were changing over time, and what that would mean. Can I get it sort of right?
Yeah. The answer is yes, but I don't know the details. I mean, this is the ratios we have today, and it was somewhat different, it is thought, in the early universe. But I'm not an expert on those sorts of details of the model. Of course, we're making our measurements in part today, but in part with instruments that go back in time, because it's the time it takes the light to get to us, such as what we were saying for the James Webb Space Telescope. And I think the thought is that, in fact, those proportions have been changing, but I'm sorry I can't give you more details.
And not on your time scale. They're not changing. Okay, so I think we will wind up now. So let's thank Art again for a wonderful talk.
Thank you, sir.